this. I don't like it as well, but it does work. Okay, so guys, again, back to the conversation. Here's what we're going to do today. Well, first of all, here's where we are. So at this point, we understand that we can assign energies to the energy levels, and when these electrons go from a higher to a lower energy level, the difference in those energies is radiated as light. We can take energy, figure out frequency, figure out wavelength. We can work that in all sorts of different directions. This is where we are right now. You guys good? Okay. Now, guys, here's what happened. Whose model of the atom is this? Well, this is the Bohr model of the atom, right? And as Bohr was studying this planetary model of the atom, they started to see some interesting things. One of the things that they found is this. If we have an electron in this energy level and it falls down to this energy level, it doesn't necessarily always release the same energy of light. What they were finding was that the electrons that are in these energy levels are actually not behaving as if that energy level has one specific energy associated with it. Remember, we've been doing this negative R sub h is divided by n squared gives us the energy. And while generally that was true, what they started to find as they were digging into this deeper and deeper was that all of the electrons that appeared to be falling, for example, from energy level 3 to energy level 1, they didn't all have exactly the same energies associated with them. And what they began to hypothesize was that these energy levels were actually composed of sublevels, S, P, D, and F, right? So guys, we began to see some spectral evidence that was seeming to indicate that it wasn't quite this simple. That this seeming structure of orbit 1, orbit 2, orbit 3, orbit 4 maybe wasn't quite complete. That it was beginning to look like these energy levels, these orbits, had substructures. And they weren't quite sure how to describe that, but they were finding out that this was appearing to be the case. But then alongside that, they were also, thank you Schrdinger, beginning to realize that there's this tight connection between subatomic particles and waves. That particles release waves, but then Heisenberg and Schrdinger started to suspect maybe these particles were waves. Now guys, let's pause there for a second. Do you remember how that logical progression went relative to the Heisenberg uncertainty principle? Or should we talk about it? Well, it's not quite, the double slit was sort of an offshoot of it, but can you in your brain marry together the Bohr model, the wave model, and how Heisenberg played a part in that? Or should we talk about it? Okay, so guys, this is the idea. So Bohr is studying electrons like little particles moving around the nucleus, right? And in order to do that, you've got to be able to figure out where these electrons are and where they're going. And that works fairly well. But then they started to realize maybe it's not that simple. There seems to be some substructure. But then as Bohr continued to try to push this envelope in terms of refining his model, what he began to find out was his data started to fall apart. Is this starting to sound familiar? And Bohr was getting back some real anomalous data that was beginning to suggest that maybe in fact these electrons are not particles moving around the nucleus. Because guys, and this is the bridging thought, think about this, if you're going to study electrons like they're planets moving around the sun, that requires that you be able to know where that electron is and where it is going at every moment in time, right? If you want to track something, you've got to be able to not only know where it is, but you've got to be able to know where it's going. Well, it turns out that as Bohr was developing these models, he was finding quickly he wasn't able to do that. So then along came Heisenberg. And what did Heisenberg propose? It's called the uncertainty principle. And Heisenberg said this. He said, Bohr, your math is good. Your data is good. The problem does not lie in your experiments. The problem lies in our understanding of atoms, because it turns out that these electrons will not allow us to track them. Do you remember how he said that? It's called the uncertainty principle. Do you remember? And so that was the thing that grew out of this, was the idea of probabilities. But why was the idea of probability necessary? And the answer is this. Guys, there's a fundamental principle in our universe that says you can never know, and I'm going to use the big boy terms, you can never know the exact position and momentum of an electron simultaneously. Do you need to write that down? Do you not remember that? So let's write it down. So guys, this is what is called the Heisenberg uncertainty. This is called the Heisenberg uncertainty principle. And it says you can never know the exact position and momentum of an electron at the same time. So guys, first of all, let's talk about what this means in layman's terms, and then we'll talk about why. So, obviously, well, maybe not obviously, position simply means location, right? Where the electron is. What does momentum mean? Well, it does have to do with fast, but it also has to do with direction. What's the opposite of scalar? It's not scalar, it's vector. It's also got direction. Fundamentally, it means this, where it's going. So, guys, basically what Heisenberg said was we will never be able to tell where an electron is and where it's going simultaneously. Now, guys, understand that's not because our science is bad. It's because the universe is structured in such a way that we don't get to ask the question. The universe is fundamentally unwilling to allow us to know this. Now the question is why? And the answer, guys, is because electrons don't have position until you locate them. We didn't talk about this last year. It was in the video, but we can talk about it now. Guys, electrons don't actually exist. Electrons are excitations in an electrical field that only has probabilities of existing. So these things that we call the S and the dumbbell-shaped P's and the cloverleaf D's and the whacked-out F orbitals, guys, these are simply locations of highest probability. So what does this mean? Well, what it means is this. If you've got an electron traveling around the nucleus of the atom, it is actually not doing that. That electron could be here, and then it could be over here, without traveling through the space in between. Guys, that electron can be in all positions at once. That electron can be in no position at once. That electron can spontaneously appear and disappear. Guys, electrons are not particles. They are simply probabilities, and those probabilities are described as waves. Now, guys, understand there's nothing in our world that behaves this way. But you've got to understand electrons fundamentally don't exist. Until we do what? Until we look for them. And guys, when we look for an electron, there's something weird in our universe that forces that electron to choose a position. But here's the problem. In finding the electron and forcing it to choose a position, we have now affected the electron, and it will not go where it would have gone had we not found it. So we can know its position, but then we won't know where it's going. And if we know where it's going, then we won't know its position, because making it choose a position changes its momentum. So guys, there's something fundamentally weird about electrons that doesn't allow us to both know where they are and where they're going. And that weirdness is the fact that they don't exist until we look for them. And prior to that, they are simply probabilities that are spread out around shapes that happen to look like all these pretty things. So, guys, with that said, that is where Schrodinger then got super brilliant. I won't spill. So guys, here's what Schrodinger did. He said, okay, if we can't know where these electrons are because we can't, finding them messes them up, thank you Heisenberg, what Schrodinger did is this. He said, well, we need a new way to think about electrons. And Kami, this is where we start talking about probability. And so Schrodinger says, if we can't study electrons as particles because they're not until we study them, what if we think about them as waves? And it's not that the electron is a wave, but the probability of the locations where we find those electrons take on volumes that have wave-like properties. And this is where we then get things like the S and the P and the D. They did it. Wow, look at that F. That's cool. And the F orbitals. So guys, understand that that does not mean that these electrons are traveling in spherical or dumbbell-shaped spaces. What that means is the location, the probability of locating an electron is greatest inside this volume, and if we go to look for it, chances are good it's going to be here, or it's going to be here, or it's going to be here. Do you get the idea? And guys, it radically changes the way that we think about electrons, because now they are no longer Bohr's particles traveling along orbital paths. They are now probabilities that occupy, when we look for them, these crazy wave-like spaces. So guys, thoughts or questions or things that you need to clarify about that? Yeah?
The orbital shape.
Yes.
So is it like based on that, where it's like the probability lies? Is it like the surface of the perimeter of the orbital, so like inside?
That's a good question. And to be honest with you, there was probably a time in my life when I knew the answer to that, and it's faded into the background. So these shapes come as the graphical representations of Schrödinger's wave equations. And you're right that, for example, if we just look at the 1s orbital, this is the region of greatest probability. And it's not an even distribution. There is a maximum. If I remember correctly, the maximum is actually the boundary of the volume. And realize this should be three-dimensional. It should be a sphere and not a circle, right? But I'm going to go with that's the answer. The boundary is the place of greatest probability. Yeah, I believe that. I'm pretty darn sure that's the case. Go ahead, Catherine.
Okay, so you know how last year we learned that like the electrons, that's where they sit, kind of?
Yeah, because I didn't want to talk with you about excitations and electrical fields and things, but okay, yeah.
So now it's just like, that's just, okay, so they can be out of that?
Oh, absolutely. Yeah, for sure. So what we're talking about is probabilities. So the first two electrons in an atom will probably be in a small sphere. The next two will probably be in a bigger sphere. The next six will probably be in these dumbbell-shaped spaces that are about the same size as the sphere. So these are just the volumes where these electrons most probably will be.
Okay, and we've like drawn those shapes just from like the probabilities, like it's not like there's an actual force.
That's exactly right. Yep, that's exactly right. Go ahead, Brandon, just a second.
You gotta do the experiment that determined that you can't know their exact location unless you force them.
Heisenberg? Is that the...
The one guy did the experiment and he found that Einstein was wrong it was recent. It was in like, it was the guy who's like, as a grad student, I hated quantum.
Oh, yes, yes, yes.
Read research.
Yeah, to be honest with you, I don't know. I'm not sure. I do know this, that what you asked was, how do we experimentally determine that the Heisenberg uncertainty principle is correct? And Heisenberg initially didn't do it experimentally, and is apparently from the video, they referenced an experiment that supports it. Heisenberg's initial insight into this was strictly mathematical. He was trying to plot through matrices, you know, those weird spreads of numbers that they barely teach you how to do in math classes. He was actually trying to study the position and momentum of these electrons through matrices math. And he was finding that he was getting all these wonky answers that made no sense, and it was driving him crazy. And he actually had this moment where he was like, the problem isn't my math. The problem is I'm trying to describe something that is undescribable. He described it as if he was multiplying 2 times 3 and got 7. It just didn't make any sense, that the results of his math didn't make any sense. And the reason is because the unknowable nature of electrons. The experimentation I'm not sure about. Catherine, just a second, go ahead.
All right, so with those,
Uh-huh.
their probabilities, what does the probability work like? If I have an electron in the, let's say in the valence shell, they could have a probability of being out here, but that probability is very low.
Mm-hmm.
What about in a lower orbit? So,
It's the same thing. So you could have a mercury atom with 7 energy levels, and its 1s electron could be a mile away.
so there's no, like, we talk about that, like, you can't have an electron in between them, but positionally you can. So it's like technically in like the 5th orbital, but it's actually out here. Like, does it
No, it totally makes sense. So, I mean, so right, if these electrons can be anywhere, can't they also be in here where we've said they can't be? And the answer is yes, but they don't hang out there.
Yeah.
Right, and so when we actually do experiments on these things to measure their energies, functionally they don't spend enough time there for us to get data that supports their presence. So the probabilities are so low, they're approaching 0. Go ahead.
Also, Daniel's question is,
Mm-hmm.
so is it true that orbitals are kind of like shells where there's only distinct orbitals and you can't have like half orbitals? Like,
I don't know if I follow you.
because with the electron like energy circles,
Mm-hmm.
you can't have like electrons in between. Is that like true for orbitals where like there's only distinct orbitals?
Yes. So and forgive my drawing skills, but if you've got your p orbitals, you shouldn't find electrons in these spaces.
And you can't have, like, orbitals don't change, like, the actual shape of the
They do not.
orbital.
No. Yes, they do change when they bond, but we call that hybridization, and we'll get there. But in an atom in its ground state, the shapes of those orbitals is static. Yeah. Guys, are we okay to make the transition then? Okay, so then guys, what we need to do is we need to think about these atoms in new ways. And so Bohr, as you already know from our Rydberg constant divided by n squared, Bohr proposed this idea, that there's a quantum number n which tells us the size of the orbital. And guys, I'm going to suggest that you not try to write this down. Well, how's this going to go? You know what, we're just going to do this. Oh, are those mine? Must be. We're going to do this and see how far we get. No, we'll see. Let's just get going. Okay, so guys, we've got this principal quantum number n that tells us the size of the orbital. But guys, this is familiar to us. We've seen this. N is 1, n is 2, n is 3, n is 4, n is 5, right? Okay, so this is familiar territory. And what we know is this. As n goes up, we know that the size of the energy level increases. We know the value on the periodic table goes 1 through 7. We know the capacity increases by the 2n squared rule. And as n goes up, guys, stop writing and look, and then I'll let you write this down. As n goes up, the size goes up, and the energy goes up to a maximum of what? 0, right? The maximum energy of an energy level is 0. See that connection? And then, guys, the capacity goes up as given by the 2n squared rule. Do you want to write this stuff down? All right. I'll wait. You already have this in your notes from last year. Then you were in Call's class. Or, no, you're right. Probably Hart didn't share in these. You were in Israel, right? Where were you? Who was in Israel? Somebody like went over to the... No, somebody was over with their parents at the Jerusalem Center. I guess that wasn't you. You guys good? Okay, so then, guys, again, as Bohr is fleshing out this model, as he's pursuing this idea of energy levels, he found evidence that the energy levels were more complex and that these electrons were not allowing themselves to be studied in such a manner. Heisenberg uncertainty principle. Along comes Schrodinger via his wave equations and says that these energy levels are actually broken down into sublevels. These sublevels have different shapes. Those shapes are given by the letters S, P, D, and F, where the S are spherical, the P are dumbbell shaped, the D's are the clover leaves, the F's are all whacked out. But there's a limit to the number of sublevels in an energy level. And that limit is N. So the first energy level 1 sublevel, the second energy level 2, the third 3, the fourth 4, and so on. Is it starting to come back to you? Canned. Then, guys, these sublevels are broken down into orbitals. The orbitals are the spaces that can be occupied by 2 electrons. And then remember, guys, we've got to get past this problem that because electrons have similar charges, they don't want to pair up in orbitals. And we explain that based upon what is called their spin. Their spin quantum number allows for this idea that in order for electrons to pair in an orbital, they have to have opposite spins. I'm going to let you be lost for just a second because this is all going to come together in just a moment. This is the fire hose overview, and we're going to dig into this. And if it doesn't make sense then, we'll talk. So guys, this spin quantum number has 2 values. Up, which is +1/2, and down, which is -1/2. And again, guys, if you're in Catherine's position right now and you're going, it'll come. Here's what we fundamentally know. Energy levels tell us the size of the cloud. They go 1 through 7. They're the orbits in the Bohr model that aren't that simple. These energy levels are broken down into sublevels. There are 4 types, S, P, D, and F. The S's are spherical, although S doesn't stand for spherical. It actually stands for simple. The P's are dumbbell shaped, the D's are clover leafed, and then the F's are crazy. But there's a limit to how many there can be. The first energy level has 1, the second 2, the third 3, and so on. These sublevels are then broken down into orbitals. The orbitals are actually the spaces the electrons occupy, and an orbital can contain 2 electrons. Those 2 electrons, in order for them to pair up, have got to have opposite spins. The reason is because electrons are both negative and they want to repel. But you may remember that electrons also are magnetic. They have a north and a south pole. And so in order for electrons to pair, they will actually flip over. One will be north pole up, the other will be north pole down. Now they're north pole to south pole orientation, and that allows them to attract in a way that allows them to overcome the repulsion of their charges. Is that coming back to you as well? Okay. What's up? Why wouldn't it? Right, but they're still, forgive the term, but aware of each other. And so if this electron's over here, and again, to make this make sense, we got to talk about them as particles. If this electron is over here, it will influence the orientation of this one, and vice versa. So they will always be out of phase in terms of, actually the term is angular velocity. Their angular velocities will always be out of phase because this one is aware of this one, and as one turns, the other turns. Even if it's like this, they'll always be opposite of each other in terms of their north pole orientations. The thing that's really interesting is if those oppositions caused by, so it's interesting, I don't know how to do this without doing a lot of physics, but imagine if this electron is moving like this, and if its north pole is pointing at a 90-degree angle to its plane of motion, it will have a different energy than if its plane of motion is actually in the same plane as its travel. And with really good spectroscopes, you can resolve the difference in energy of those electrons based simply by their magnetic orientations. It's pretty crazy. So, go ahead. Well, don't worry about M, worry about orbital quantum number. And that's what we're yes, and that's what we're about to do. Give Catherine a hug. You guys are now in the same lost position. Or Catherine, give him a... Okay, so let's do this. Again, guys, if you're lost right now, let's pull these pieces together. And this is maybe where this starts to make sense. And now let's start asking and answering questions. So guys, energy level, sublevel, orbital spin, yeah? How does this fit together? Well, guys, remember what we did last time in class. Don't try to write this down. I don't care if you want to, don't. You can't keep up. So guys, it goes like this. So this is a core sample of an atom. If you don't remember what that means, it means you've got the nucleus, you've got the energy levels. If we were to drill down into this, at the bottom would be the nucleus, and then we would have these rungs that represent the energy levels. So that would be this. And so this is an energy level, this is an energy level, this is an energy level. That's an energy level. You get the idea? Okay. And then, guys, this space is not to scale. It should actually look more like this. If this is the nucleus, the first energy level is way out here, then the second, then the third, then the fourth. They're always getting closer together, but in order for that to work here, you'll notice these do get closer together, but I would have had to put the nucleus on the floor in order for it to be to scale. So, with that said, guys, let's start filling this out with energy level, sublevel, orbital stuff, and let's see how you do. So, guys, starting here, this is energy level, this is sublevel, this is orbital. So here we go. We've got the 4 energy levels. What should this go up to? 7. We're going to stop at 4, but we've actually got 7 energy levels for all of the elements that we know about in our universe. And then, guys, these energy levels are broken down into sublevels. What are the 4 sublevels? S, P, D, and F. Good? Okay, so guys, the first, and actually before we do that, let's talk about electrons. How many electrons are in the first energy level? 2. And then the second, do you remember 2n squared rule? 2n squared rule, plug in 2, not there. 2n squared, plug in 2. 2 squared is 4 times 2 is, there you go, is 8, is a dot, is 8, and then 18, and then 32. And then it goes up from there. Okay, so now guys, let's move over and let's talk about sublevels. So the first energy level contains how many sublevels? 1? Is that okay? So first energy level contains 1 sublevel. It's an S sublevel, so we call it the 1s. Remember that? Now guys, if there's two electrons in the energy level, but only 1 sublevel, then those 2 electrons have got to be in this sublevel. Then when we talk about orbitals, an orbital is the space that is occupied by 2 electrons. So these 2 electrons, there we go. So these 2 electrons in the 1s sublevel only need 1 orbital to house them, and that 1 orbital happens to be a spherical orbital. And so the first energy level contains 1 sublevel. It's an S sublevel. That S sublevel contains 1 orbital. That orbital happens to be spherical, and that spherical volume denotes the place where that electron, those electrons, will most likely be found around the nucleus of the atom. The probability. You okay? Okay. But guys, remember, we don't draw those when we draw these for orbital filling diagrams, we simply replace these with boxes, but we'll do that in a minute. Okay, so now we're on to the second energy level. And the second energy level contains 2 sublevels. 1 is S and 1 is P. Now, guys, we can talk about this. Why is the S lower than the P? Why? Lower energy. Guys, we never talked about this, but the units on the y-axis are energy, right? We can figure out these energies. So we could come along and we can go negative r sub h divided by n squared, and we can figure out the energy of that. And then we can go negative r sub h divided by n squared, and we can figure out the energy of that. But guys, when we do that, is that the energy of the S or the P sublevel? And the answer is neither. The S is a little bit lower than this value, and the P is a little bit higher than that value. It's not truly an average. I think it's skewed towards the P, but I'm not positive of that. I don't think it's because it's more, but I do remember it not truly being it. But it doesn't matter. I mean, it does matter, but not for what we need to do. We just need to understand that this negative r sub h divided by n squared gives us the energy of the second energy level, which is neither the S nor the P, because the S is lower and the P is higher. Is that okay? Okay. All right. So now, guys, let's talk about electrons. So when we talk about electrons, we've got 8. We've already established that 2 go in the S. So how many have got to go in the P? The remaining 6 to give us 8, right? So now when we look at orbitals, how many orbitals does it take to house 2 electrons? Well, that would be 1. And then how many orbitals does it take to house 6 electrons, given that each one can hold 2? That would be 3, and they're dumbbell shaped. Do you remember that? Okay, so now here's what we've got. Guys, we've got 10 electrons, right? 2 in the S, and we've got 8, or I'm sorry, 2 in the first energy level and 8 in the second energy level. The first 2 electrons are in the 1s orbital, and it's shaped like a sphere. The next 2 electrons are in the 2s orbital. It's shaped like a sphere. The next 6 electrons are most likely to be found in these p orbitals, which are dumbbell shaped, oriented 90 degrees to each other. Okay, so the question then becomes this. What does this look like with the understanding that all of these shapes are really all around the same nucleus, Because these are all the same atom. And guys, the answer is this. Do you remember? This is neon. Guys, quite literally, this is what we think of neon looking like. So what is this? That's the 1s orbital with the probability of, this is the highest probability of finding the first 2 electrons. Then guys, what's this dude? The 2s. You'll notice that it's an s, so it is still spherical, but it's in the second energy level, so it's bigger. Then guys, we've got 1, 2, 3 p orbitals. Those p orbitals are approximately the same size as the 2s, although you will notice that they're a little bit bigger than the s because the p is a little bit higher energy than the s. That's why it fills second, the s first, the p second. But guys, this then describes the locations of highest probability of finding the 10 electrons around a neon atom. Now, are they really there? No, until we look for them. And when we look for them, they then behave as particles, and the chances of us finding them in these volumes is almost certain. These are the places these electrons are. You get the idea? Okay. So then, guys, where do we go from here? Well, guys, remember, whoa, why are those over there? So, guys, these boxes got shifted. I don't know what happened, but they should, they should be like this. Because remember, that's actually the way we draw these electrons. We don't draw spheres. We don't draw dumbbells. We actually draw boxes, and then the arrows represent the electrons in the orbitals. And what's the significance of one being up and the other being down? Opposite spins, which really means opposite north poles, right? Okay, so then, guys, we go to the third energy level. The third energy level has got 3 sublevels, S, P, and D. 2 in the S, 6 in the P, then the remaining 10 are in the D. How many orbitals does it take to house 10 electrons? 5. And they actually, those should be together. They actually look like this. These are the, oh gosh, sorry. Those are the, these are the 5 D orbitals. I think that our extra credit person over here did a nicer job of this. They actually, all around the same nucleus, actually look like this. And those are the volumes that those 10 electrons occupy in the D orbitals. Is that coming back to you? Then, guys, we move along to the 4th energy level, and this is where things get freaky because the 4th energy level has 4 sublevels, S, P, D, and F. But we remember that the 4s actually tucks inside the 3D. The 4s is actually lower energy than the 3D. Therefore, it fills first. So the electrons go 2 in the S, 6 in the P, then 10 in the D, then 14 in the F. But they actually don't fill in that order. They go 2 in the S, 10 in the D, then back out to the P for the 4P. Remember that? Okay. So then, guys, we had this magic moment where we realized that this is important, and forgive these things for sliding, but we need to know this order. They go 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, and so on. And we had that magic moment where we realized that this is the order of organization for the periodic table. Do you remember? Where we said that all we've got, and I'll just do it with the laser, guys, where we said this. We said the energy levels are the horizontal rows, and then we've got the S and the P and the D, but it's D minus 1, and then the F minus 2. You know what? I want to bring this down. Not my first rodeo. And so we've got this where all we've got to be able to do is count, right? So electrons 1 and 2 are in the 1s, then electrons 3 and 4 are in the 2s, then electrons 5 through 10 are in the 2, is this coming back to you, the 2p? Then electrons 11 and 12 are in the 3s, and then these guys are in the 3p, and then the 4s, and then what about these guys? 3d, and then the 4p, and so on. So guys, that's the organization of the periodic table. Is that all coming back to you? Yeah. Filled or started, because those answers are different. So let's go down and look. So when we get down here, the electrons 55 and 56 are in the 6s. Then electron 57 is in the 5d. So the 5d starts, if you will. Then electron 58 is down here, and that's in the 4f. So one electron gets placed in the 5d. Then the next 14 electrons go in the 4f, and it gets filled. Then electron 72 actually ends up back in the 5d that we've already started, and then that fills. Is that okay? Go ahead, Brian. What is a big gas?
Noble gas. Why is it noble gas? You say noble gas.
Look at those big gases. Those are big. That's a big gas you got there.
But if you do nickel, it goes to higher one.
Yeah, so here's the thing. What you're talking about are noble gas abbreviations. Guys, let me tell you what we were going to do, and then let me tell you what we are going to do. The intent, and this is not in any way a slight against any of you, the intent was that we were going to rocket through this material pretty rapidly, and that we were going to get to noble gas abbreviations, orbital filling diagrams, things like that. It's becoming apparent that it would be worth talking about those things. Well, maybe I should ask, do you guys feel like, given what we just went over, you guys could go back and do orbital filling diagrams? You do? Okay, then never mind. Let's answer your questions, and then, so let's do that. So how do we do, let me turn on the lights. How do we do these orbital filling diagrams? Well, let me do this, and then let's talk. So guys, say for example, we want to do, let's just do noble gas abbreviations. So say we want to do the noble gas abbreviation for silver. Okay, so what we're going to do is we are going to go back to the previous noble gas, which in this case is krypton. So what we're going to do is we're going to go Kr for krypton, like so. Then going to silver, in addition to krypton, we've got these two electrons, which are where? The 5s. So that would be 5s2. Then, to get to silver, we're in the 4d, and that would be 1, 2, 3, 4, 5, 6, 7, 8, 9. So that would be 4d9, and that would be the noble gas abbreviation for silver. Now, if you wanted to do that as an orbital filling diagram, you'd have to go all the way back to the 1s and the 2s. But eventually, when you got out here, what you would find is you'd have 2 electrons in the s, and then 1, 2, 3, 4, 5, 6, 7, 8, 9 electrons in the d, which then especially makes sense because silver is 1 box short of the end of the 5d, which is that one open space. Okay, now guys, with that said, because I know you're going to run into it just a second, in the homework, guys, if you look up, and I picked silver on purpose, if you look on our good periodic tables, you will actually see that this is not the noble gas abbreviation for silver. The noble gas abbreviation for silver is actually this, 5s1 4d10. Why? What is actually going on? What would 5s1 4d10 look like? Well, guys, let me rewrite it. 5s1 4d10 actually looks like this. So, guys, this is what silver should look like. This is what silver does. You know what? I should do that differently. Sorry, hold on. Let me do that differently. This is what silver should look like. This is what silver does look like. Why? What's going on? So one of the electrons from the S is going where? Into the D. Guys, why does it do that? Why does anything happen? It releases energy. Guys, it turns out that this structure, where you've got 2 electrons in the S and 9 electrons in the D, this structure is higher energy than this structure. So one of the electrons jumps out of the S into the D. Why does that make it lower energy? Because now the D is full. It's lower energy to have a full D and a half full S than it is to have a full S and a randomly structured D. So this is lower energy. So now, guys, the question is, so what? Well, guys, which of these electrons are valence? The S or the D? Just the S. These are the valence electrons. So, guys, if you look at silver on the periodic table, does it go +1 or +2? You should know that. Guys, silver only goes +1. Why does silver go +1? Because it can lose this electron. Why can silver not go +2? It doesn't have 2 5s electrons. One of them jumps into the D, so the only one that it can lose is the only one it's got out of its valence shell. So now you're going, how on stinking earth am I supposed to know that if this is the periodic table I get to use on the test? No, the answer is, guys, you'll either know it from inference or they won't ask. So if you saw a question on the test that says, why does silver only go +1? They would expect you to be able to draw the orbital filling diagram and realize that that electron must be jumping. But you will never see a question on the test that says, what are the possible oxidation numbers for silver? So you don't have to be able to memorize when this jumping goes around. You just have to be able to explain the implications of the jumping. Does that make sense? Okay. So, guys, that's kind of where we are. You got to be able to draw Lewis dot structure, or I'm sorry, you got to be able to draw noble gas abbreviations. You got to be able to draw orbital filling diagrams. You need to understand that stuff. It sounds like you're thinking if you just have some time, it'll come back to you. Okay, so guys, let's do this then. Here is a little thing we like to call your homework. Looks like this. So, guys, with that said,